welcome everyone to whoever's listening to this particular podcast on YouTube, Apple, Google, Spotify, or any other platforms. I am Shah, and I invite engineers, researchers, and entrepreneurs to talk more about their current work, insights about their journey, and getting started with it. Po-Shen Loh is a professor of mathematics at Carnegie Mellon University with research interests in combinatorics, probability theory, and computer science. He is also the coach of the United States International Math Olympiad team, and it was under his guidance that he led his teams to win with the first place in 2015, 2016, 2018, and also in 2019. He's also the founder of Expii, an online platform that teaches young students basic concepts of math and science. He's also the founder of an app called NOVID that has a very innovative approach of contact tracing in order to reduce the spread of coronavirus, which I think we'll learn more about from him in this particular podcast. So, Po, welcome to the podcast and thanks for being here.
Oh, of course. Nice to talk to you.
All right. So, just to start learning more about you from a background perspective, can you tell us how did you discover your interest in mathematics and what was the point that you decided that you want to pursue this interest on a serious scale? You're a professor now at Carnegie Mellon. So when did you decide that you had an interest for this and what was the point you realized that you want to take it on a very serious scale to being a researcher?
Well, that's an interesting question. I mean, I think I myself still don't exactly know what I do, so I'm not sure I've made any very firm decision to do the same thing. However, if you ask like when I decided to get into these technical fields, I think it was when I was fairly young, maybe in elementary school. My parents taught me mathematics at home. My mother taught me mathematics at home. My father gave us interesting, challenging questions to think about that used mathematical ways of thinking. And then when I went to middle school, that's when I found out that you could get really interesting challenges in these subjects. I found, well, actually, middle school math competitions found me. And now, when I was doing these competitions, I found that there are some really interesting technical questions, mathematical, which I didn't know how to do, and that attracted my interest. I'm actually attracted to hard things. Sort of, if I can't do it, I want to know, well, how can you do it? And I guess there's a lot of such questions in technical fields. So I just kept like solving problems that other people had given. That's how I did math competitions. I went to university. I would do homeworks. I would do exams. And it was later on when I learned that there are very interesting questions where it's not that people have given them to you, but that you're starting to ask the questions yourself. And that was my biggest transition. That was after finishing graduate school and having to ask my own questions. And ultimately, that's what I do now.
Right, right. And one interesting thing about your profile is I have seen not many academic researchers have such a diverse portfolio of interests. I have seen you teach young students, which are like from high school till even like being a professor at Carnegie Mellon University. You're the founder of two very small startups, but still they have very innovative approaches of approaching much of the similar problems, but in a very innovative style. And also you're the coach of International Math Olympiad. So, what is the reason for you taking out your interest from your standard mainline research? Is it something that you find interesting about exploring the breadths of topics? And if it is very interesting, like what is one thing that you have realized that if you explore so many topics in different senses, what is one thing that you have learned?
So a lot of the work that I do is actually united by the idea of trying to have some kind of actual impact.
Hmm.
So I am very attracted to hopefully doing something that matters in this world. Where it matters, it means that it has affected some people's lives, hopefully more people into the future as well. And so, and so as I look at these different kinds of activities, definitely by being a research professor, I can discover hopefully some new ideas in mathematics that has some impact. I hopefully can teach some really really capable students. That's also great. And but when you think about what I do with the coaching and the working with younger talent, that's all about building up talent so you can have more impact there. And then these other two startups that I work, well, they're the same organization, but the Expii.com and the NOVID, these are all efforts to try to actually reach the real world. But now, why is it all technical? It's because technology lets you multiply your power. It makes it, I don't mean power in terms of controlling the world. I just mean any sort of force that you do, any sort of effort that you do, technology can help you multiply it. So ultimately, I use the mathematics to think of new ways, innovations, ways that you could have a significant impact on the world by having come up with some idea. And then suddenly there's this other arm of my work which tries to make those things actually happen.
Right. So it's more like a thought that you keep in, like when you are trying to deal with these kind of theoretical problems, you always try to also associate what can I use it for in a practical setting. And if you happen to have such kind of problems revolving around you, you will try to make a solution out of that particular theoretical
Yeah,
approach.
yeah. So it's sort of like that. I mean, I don't exactly want to be a solution looking for a problem. That doesn't work very well. But I do like to be building up a general capability, a whole bunch of different capabilities. And of course, you get that from research, you get that from learning other things. But I also am always looking to see what problems are in the world. And then if I ever start to notice, oh, here's a problem, and oh, wow, I actually have an idea, right? If you have a lot of problems and a lot of solution methods, eventually you find, let's connect them. And then thankfully, because I'm at a great place like Carnegie Mellon University, you can find amazing people, students at Carnegie Mellon who are brilliant. And then maybe you start working together and you can actually do something.
Right, right. And I got a chance like, when I was doing a little bit homework about you, I got a chance to look at your YouTube channel, and a lot of things you have posted over there has like something that's called Daily Challenge with Po, which is something very interesting. Even I got a chance to look at few of the challenges that videos that you have over there, and they're really interesting. And this really intrigued me. The next question was, even back when I was in high school, math and a lot of other students with me, math was not something that they would directly find an interest. It would be something more like, if I have to do it, I will do it, and I can score well in a particular exam. But not a lot of students explore math for the beauty of it. Do you think, is there something to say, because even when I came into college, I realized that math is really ubiquitous. Like, pick up any engineering discipline, you will realize applications of math in some way or the other. Is there something you can say about instilling the interest in mathematics from us for to a student in a much more natural sense, regardless of whatever they do? They could do something else later in their life, but is there something to speak more about of instilling that perspective, that how what really mathematics is? It's not just addition and multiplications. It's not something very boring that a calculator or computers do, but it is something more than that. Can you speak more on that, because you have been teaching a lot of things in a very creative sense, I would say a fun sense. So what would you speak to that?
Yeah, so that actually I can sympathize with that journey because definitely when I was earlier in my life, I saw that math was something that you could do to get awards or that you could use to get into university or that you could use to satisfy your graduation requirements. Like that's what I saw math was good at. And I also could see that I could help people do that. And sometimes I would even teach people how to do well on tests, like test preparation for getting high marks. That's like the goal of everything. And as I progressed further, I started to realize that, oh, math is actually also a beautiful subject. And okay, that's great. And I went and told people it's a beautiful subject. A lot of people said I got no time for any beauty in the math. Okay, nice that it's beautiful, but no, no, thank you. Okay, and then I kept thinking a bit more, and it's math is applicable. But that's like telling somebody, eat your broccoli. It's good for you. Still broccoli, right? And then after a
Right.
while, I got to the stage where I am now. My current view on the point of math is that it teaches you how to invent things. And now that's actually compelling. What do I mean by teaches you how to invent things? Well, if you look at the kinds of work that I do try to engage in things where whatever we have created is hopefully called by people as innovative or something that's unusual that has not been tried before. And that's because that is my personality. I want to always try to come up with something that was not regularly done by many people before. But the only way to learn how to do that is to be practicing that. You cannot learn how to invent things by watching other people invent things and then saying, now I copy them. No, it's not invention anymore. Yeah. So the only way is to actually invent things. And that's what I learned from this kind of challenging math. So in fact, the way that I do mathematics education nowadays, like the daily challenge with Po-Shen Loh, that's actually our online math course. But the way I run that is I say, if you want to teach people a concept, don't. Don't tell them this is how you do it. That's the wrong way. That's a great way of having them learn how to memorize and repeat. And
Hmm.
instead, what we do is we actually teach any concept by effectively, what happens is that I pitch, I go and say, hey, here's a really interesting question. I don't think you know how to do it. In fact, you probably don't know how to do it. Give it a go. And then you let the person think for a minute, but you still don't tell them how to do it. Then you put a hint on the screen. It's a hint. It's not how to solve. Just some hint saying, maybe it's useful that there's this thing called Pythagorean theorem. Think about that. Just a hint. And then you give them another minute. A minute later, you give them a big hint and say, you want to draw this little triangle here and use Pythagorean theorem on that, right? And then hopefully after the big hint, they can come up with a whole solution. But you see,
Hmm.
the goal here is you would then use the math as a vehicle to really have them constantly be thinking, how can I assemble the various tools that I have to come up with how to solve something I have no idea how to solve before? That teaches the raw art of invention. And why math
Hmm.
to do that? Because it's much harder to teach that if you try to do it with any other subject, because other subjects require more general facts, like 9.8 meters per second squared. Why? Well, because it is. And if you go to Jupiter, it's
Right.
different. I don't know what it is there. But it's just like too many arbitrary facts, or like 23 pairs of chromosomes. Why 23? Because it is. But with mathematics, there's a smaller set of things. So you can learn to invent in a sandbox, so to speak. So that's actually now what I think. I run around the country explaining to people the way you use math, the way you learn math is that you should be thinking about challenges that are sort of just beyond what you know how to do. And don't let anyone spoil it for you by telling you how to do that problem, which unfortunately most people do, right? Don't just like
Hmm.
watch someone do it and practice 10. No, spend all your time working on things that you don't quite know how to do, but are just out of reach. And then you learn invention through mathematics. Then you use the invention everywhere else.
I want to dig more onto the idea of invention, because one thing I can definitely resonate, even though I'm not definitely a mathematics person, but I think I have realized, like back in my high school, I participated, I think, 2 or 3 times in local Olympiad competitions within mathematics. And even though I didn't perform well, one thing that the reason I joined those Olympiad competitions was the questions we have were really interesting. They were not what we get in textbooks, right? They let you allow to that creativity, even though I wasn't good at it. But I one thing I realized that I missed was the intuition that for solving that problem. If somebody gave me the intuition that, okay, you need to think in this way, everything was a cakewalk. And at that point I realized it is the intuition that's the real key, I think, for a person who would be really good at mathematics. And I think that's what you are calling about invention. So can you talk more about how exactly do you think these kind of intuitions or invention thinking, or problem solving skills, I would say in normal senses, is being instilled in students? Do you see developing in students? Is it through raw practice of similar kind of questions, or do you use some kind of other latent knowledge to be instilled into the students, that they get inspired to think out of the box, or maybe on the right intuitions? Is it just
Ah,
practice, or is it something that's not just in practice and words of mathematics?
so I think that it comes from constantly working on things that you don't recognize. So you see, this is actually the opposite of what a lot of people do. A lot of people are spending their time practicing. A lot of people will go and find all the past papers for the last 10 years and just want to have practiced all of them so that they can hopefully recognize the problem type. So that they can hopefully recognize the problem type when it actually appears on the real exam, and hopefully they don't have to think. That's actually their objective. But that's not how I learned math. I found that boring. So I actually would always just go and look and see, can I go and play with questions for which, hey, it looks fresh. I don't know what to do. Oh, now I'm interested. I want to try it. Yeah. So that's actually how you develop this ability to fight against things you haven't seen. And then when we talk about invention and intuition, what makes invention hard is that if you haven't seen before, how do you even start thinking? Right? You don't know. You don't know what you should do. And some people will then say, well, that's where the intuition comes in of in such situations, maybe you could try going that way, or maybe you could try going that way. And this is useful because there's too many options. A lot of people don't know what to do because they don't know which direction to try first. And then they just give up and say, too much. I don't know how I would approach that problem. And then if you do this enough, you start to develop a smell for something. And you say, as I'm looking at this thing, it smells like we're making progress. Maybe I should keep pushing it more, as opposed to saying, "Hey, I have not succeeded yet after thinking for so long. Maybe I give up." But you need to have this. You need to have this smell of, "Hey, it seems like we're getting closer. So I'm going to just keep going, even though I'm not making any progress." And that's what I've noticed. Somehow, like the thing is, a lot of people just get scared and just decide not to try, or they give up too early.
Right, right. And I think this is parallel to what you said in one of the articles, or I think interviews, when you were appointed the coach or the of the Math Olympiad team over here in United States. One thing that was interesting that you said is your focus wouldn't be ever to win the competitions. It was just trying to, I would say, instill these kind of inventions. Is that something parallel to what you're saying right now? Is it something that you won't train those students to win the competitions, but rather thinking about along the lines of these invention problem solving skills? And do you
Ah,
think do you think that is still relevant as of now? Like now, down the line you have successfully led people to win 4 competitions in this, I think, 4 years or 5 years. And do you think that idea of not aiming on the competition is still relevant and focusing more on the invention part of it, like solving the questions just for the sake of curiosity, rather than forgetting that okay, we are in a competition?
Oh yeah, so I don't ever want to focus on the competitions. I just feel that's too narrow, and these are students who are very high capability. So if we just focus them on something that's not narrow, that's sort of wasting the talent. They could do a lot more interesting things later. Actually, the specific thing that I often say is when the Mathematical Association of America was appointing me to take this leadership role, I told their executive director, I'm much more interested in hopefully reading about some great thing that some of these students do in 20 years in the New York Times. And that's what I think is the ultimate trajectory we should be hoping for the people who are doing the best in any particular metric right now. Now, that's a little bit different from invention because I'm actually fairly confident that anyone who goes through the math competition track to that level is also very good at invention. I'm not the only one who figured this out. In fact, lots of people figured it out before me. That's why all of these Wall Street firms and tech companies all try to hire these people because they know that these people, you give them anything, they'll figure out how to solve it. So
Hmm.
what I was more interested in there is you have that you have that ability to invent. Now, could you use that to go and invent something that could make some difference in this world? And that's actually why I do a bunch of my work, which is impact also, with the hopes that it won't just be me telling people you should do this, but at least I at least I practice what I preach, you know?
Yeah. Yeah, yeah. Talking more about your work, I think I realized, even though I'm not very proficient with all of these terms, but I think most of your work revolves around combinatorics. And also, your PhD thesis that you did when you graduated from your PhD program was, I think, I'm sure it's called Results in Extremal and Probabilistic Combinatorics. So, for people who are not mathematicians necessarily, but do understand a fair deal of mathematics in general, can you explain what does combinatorics in general mean in simple terms, and what was your work during your PhD that you did as a PhD student stand for in much more simpler sense, if at all possible?
Oh, definitely. I think the way I would put it is that there are you can say that some kinds of things in the world are continuous and some kinds of things are discrete. Things that are continuous, especially in engineering, you see a lot. You'd see like the forces that are happening over time. Time is just going as a continuum, and the force is doing maybe as you're putting some pressure, the force is increasing, decreasing. You also have the notion of the signals that are coming. Maybe there's some waves coming through. Actually, those are also somehow continuous over time. These are
Yeah,
continuous things, and there's a whole subject of calculus that helps you to analyze what might happen when you have a bunch of things happening in continuous time, maybe even things like differential equations. So that's all continuous. Then there's also this other world of discrete, where somehow you make one jump at a time. For me, the closest thing that I think about a lot is called graph theory or network theory, where you have this node and that node. There are no nodes in between. They're just somehow connected. It's like myself and you. We
yeah.
are perhaps connected in this linkage graph of who knows who. And that's very
Hmm.
discrete because it goes from me to you. Suddenly, there's not a great calculus or differential equations. And in order to analyze these kinds of things, you need different types of tools. And combinatorics talks about things which are discrete in this way. Sometimes there are things like how many ways are there to do something. That's also discrete as you count the number of ways. But sometimes also that's relevant in the point of view of computer algorithms, where you want to see how many steps something is going to take. Uh, these are maybe interesting ways of counting things. So the idea of combinatorics is that you're counting things, or maybe you're making reasoning about networks. And I think a lot of because I think so much about networks, I often look at the world and I just see networks everywhere, and that just colors how I think about what you might, what kinds of solutions you might be able to come up with. I always want to think, how do we use that network structure that's out there? Which is like very, very strange. Network structures are strange. I would say, in some sense, geometry is geometrical. If I draw a circle, it's a circle. If I have some shape in the world, there's some shape in the world. But what does the shape of a network look like? If I try to go and say every single person is a node, connect the two people if they spend time around each other, you can't even draw that nicely. It'll be like a very messy thing. But as you think about these networks, you start to think about there are certain properties of networks that are often very useful. For example, how far apart are two different nodes? And how does that look if you have like a human network versus just a random network? So I'm not sure if this is helping explain, but I'm giving the
Yeah.
flavor of the kinds of things that one thinks about.
Right, right, right. And yeah, right. This is really interesting. And was it something along the lines of, so can you explain more about your PhD thesis? Like, what was the contribution that you did along the lines of, I think it's called extremal and probabilistic combinatorics.
Yeah, so on that one's more on the theoretical side, in the sense that
Okay.
we were trying to prove theorems that say, whenever something happens, then whenever you have some situation, then something else happens. I mean,
Okay.
as an example of, well, okay, I'm trying to think of one of the ones that might be the easiest to go and try to describe. Hmm. Okay, I can say this. So this is not exactly what we did inside it, but here is something which is related to this discrete mathematics. That it's not exactly what we did, but it's a precursor done by other people. What we did is something more complicated on it. But here's something that one might think about that's very discrete. It's that suppose I have n buckets, and n is some integer, some number of buckets, and then you're going to throw some balls randomly into the buckets. If you do that and you have these n buckets and you throw n balls inside them, you will typically not get all the buckets to be the same level. I just mean if they go in random
Yeah.
ones, there's no chance it would be one, not no chance, very unlikely it's 1, 1, 1, 1. And in
Right.
fact, the highest occupancy bucket, I already forgot what it is, might be something like logarithm of n or something like that. It's
Okay.
like it will be something. If you're throwing n balls into n buckets, it will not be evenly split. Okay.
Mhm.
Now, that's relevant to a computer science concept called hashing. Actually, it's related to, like, if I have some places in memory that I might want to store some things, and I'm going to
Right.
put my things in random addresses. This is actually finding out your biggest collision in a hashing environment. And then one brilliant result, not due to us, but that other people had done, was about if I make it so that when I throw the balls, I choose two random buckets that the new ball will potentially go in, and I put it in the one that is smaller with
Mm.
less things so far. So again, I've got all these buckets, throwing these balls. Every time I throw a ball, somehow I randomly choose two buckets that I might throw it into, figure out which of them has less balls, and then make it so the ball goes in the one with less. So you're trying to even things out better. I believe that this suddenly makes it so your biggest bucket is exponentially smaller. It's actually another log of n. So it's much more
Right.
evened out. But this is an example of some kind of a random combinatorial process, and we were thinking about things like this and proving these kinds of results.
Right, right. And is there a way to truly know which problems? Of course, this is for your opinion. I would say, is there a way to truly know which problems do you want to work on versus which ones definitely don't make sense, as in something that you would drop off very quickly? Because I think you can come up with a lot of problems in general, like when you are into, I would say, research, or in general research community overall. It's easy to pick up problems that might lead you to dead ends that definitely don't make sense. How do you for yourself figure out problems that you can say definitely it's just I need to continue pursuing, and I might find the results, versus when do you decide to pull the plug out? Like, is there an intuition that plays on, like, feel free to speak as a professor's perspective, or maybe just a student's perspective while you were as a PhD student. How do you decide those two things?
Yeah. So I think I should say, first of all, there's a question of which question you choose to work on, right? And it's
Right.
important to choose to work on questions for which, if you solved it, people would care. That's how it is, right? And so whenever I'm thinking about what I want to work on, I always do think, like, why should we even have anyone in the world thinking about this question? And when it was research questions, those would be defined in terms of, suppose we solved it, then suppose we try to tell other famous researchers we've solved this. Do they care? Would we have discovered something that could potentially help advance the field of understanding of this mathematical subject, or could it have some application in the real life? Since I'm doing pure mathematics for research, that real life part is usually not the most important piece. It's just, would it help advance things? And in fact, for the pure math, one of those criteria was often, how long has this problem been unsolved? How many people, serious, famous people, have tried to work on it and not succeeded? Oh, well, then maybe it's actually hard. And how natural is it? Does it feel like a question that I could say, maybe it's nice, right? And that would be how I would evaluate the pure math. But you see, in some sense, you can spend a lot of time on a question that's not useful, and still, after you succeed, no one cares. So that's why that was an important piece. These days, I spend a lot more of my time on the applied side. And at that point, it's also still just saying, suppose we work on this. Is this main problem we're working on hard enough that it would matter if we succeeded? Well, that's why I ended up choosing problems like how to help educate the world, or slash like help them have a different, more healthy view of mathematics and science. I think that's a very important problem. I'm willing to dedicate a lot to that. And the other one was, how do you stop pandemics from taking over and spreading across human race? That's also a pretty serious problem. So to me, it's like, yes, attack those. And then if you go and sit on a question for a very long period of time, you do actually figure out a lot of things. And when do you pull the plug? That was the other question you asked. That's like, when do you feel like you're not making any more progress? Right? And when do you feel like you're not even making any more partial ideas? And as long as I see that there's still ideas coming, if it's important enough, you just keep trying.
Right. So you would pivot on the incremental progress. So if you're trying to make some kind of incremental progress towards any direction, you would take that as a green flag. But if at all it is trying to backfire even in a smaller sense, you will say, let's try to deviate to some other problem, or maybe some other direction.
Yeah, and the amount of time I'm willing to still try, even with no progress, is directly related to how important the problem is. So if the problem is really important, I might stick there for a while. I mean, like some of these big things like education or pandemics, I might sit there for a month before I say I really have no more new ideas, right? But if it's something of much lesser importance, then maybe, okay, don't see anything here, let's move on.
Yeah, I think I want to talk more on that, because I think we covered two important things, which was the network theory, and also your the founder for you being the founder for an app called NOVID, which uses this kind of network theory to understand a contact tracing method, which is I think the unique thing about it is anonymous, right? Like, feel free to correct me if I'm wrong, but it is an anonymous app, so there is no point of having privacy issues into those apps. But I want to learn more about what is the intuition behind it, because although it seems very easy that okay, it's a network of big nodes of lots of people around in a physical space, but what is the challenging thing from an algorithmic perspective or the idea perspective into this app that you instilled? And what does, can you take it from the basic beginning, what does it do from a layman's perspective versus how you, being a mathematician, pulled in the idea to build this very efficient app?
Great. Okay. So I think I want to maybe explain a little bit more about how this thing works. In fact, the anonymous is a nice part, but that's actually not the revolutionary piece, because there are a lot of anonymous apps out there. The revolutionary piece is that this was an app designed to help you, the user, avoid getting sick. Now, wait a second, isn't that what all the apps are supposed to do? Well, no. If you start to deconstruct this, there's a whole notion of contact tracing and contact tracing apps. That's a procedure. Contact tracing is a procedure that has been used for hundreds of years, maybe even thousands of years, to go and help avoid the spread, maybe not thousands, but like to help avoid the spread of disease. The way contact tracing works is that you find the person who's sick, you find out who they are around, and you try to remove all those people from society against their will.
Oh.
That's tough. Okay, remember the way that the normal way of controlling disease, how it works, you find the one, the normal way of controlling disease, how it works, you find the person who's sick, and then you try to contain it. You find all the people that might now be sick too, and remove them. Wait a second, that's not something to try to help the person that has been touched to avoid getting sick. Right? What I mean by touched is, by the time you are a participant in that procedure, the intervention is not trying to help you avoid getting sick. It's to help you not get anyone else sick. Now, many people tried to make apps that would try to do this automatically, and they made them anonymous also. And somehow people didn't really want to download them. But now that you think about it, it makes sense. Because what were all these apps doing? They were all apps that would tell you when it's your turn to remove yourself from society to protect other people from you. Now, remember I said what we came up with was, we made the app to help protect you against other people. This flip of the direction actually flips the game theory. As a mathematician, we always think about, what can we do to reverse the sign? A minus B and B minus A, fundamentally different. This is actually how I look at the world. I'm often like, if you do some very small things, some things are not commutative. And if you go and figure out when you can flip signs, then really exciting things happen. So in particular, like how exactly does our app work? Actually, how would you make a tool to help you not get sick? Well, the ideal way would be if the tool can just tell you, see that person over there? That person's sick, stay away. But the problem is that that's just physically impossible. I don't even mean about privacy or not. That person doesn't know they're sick. We just don't know these things. Nobody knows. They don't know. So what we said is the way to help you not get sick is if we can tell you in advance if the disease is transmitting towards you along the network that would infect you. You see, because earlier I just said, like, I would like to avoid getting sick by avoiding that person there 2 meters away. Okay, but that's impossible. So the next best thing is to stop thinking about meters, but start thinking about physical contacts. Meaning that, okay, that's a person that I spend time with. Could it be that their roommate already has gotten sick? If so, oh, now something's getting close to me. I actually want to be careful. So what we ended up creating is just this paradigm shift of saying, measure how far away is the disease from you by counting the number of transmissions that it would take to get from that disease to you, where each transmission means that the two people had phones that were together for a long time, right? So the point is, suddenly it's not an issue of saying, hey, there's a disease 3 kilometers away. What does that mean to me? 3 kilometers, I don't know. But if they tell me it's 3, but if I knew instead, oh, actually that person is my coworker's boyfriend, and I see my coworker every day. Now I want to, 3 kilometers is a big deal, right?
Right.
And so my point is, all we did is we said, use the network theory to put a different geometry, a different way of measuring things. And once you have this different way of measuring things, a problem that was previously impossible, the impossible problem was tell you when it's too close. That was impossible because 2 meters away, that the person doesn't know they're sick. We changed the definition of close to the graph theoretic, network theoretic close. Suddenly impossible is possible. So that's actually where the mathematical insight came in. We were the only people in the whole world to go and build this thing, to actually, as far as we can tell, to even come up with this thing and then build this thing. And we are now in the process of trying to help everyone understand that there's a fundamentally new way to fight disease that was never available to human civilization until this last year.
So if I'm understanding correctly, if would it be the case like total number of nodes that you have in this network would be equal to the number of people who downloaded this app and actively continuing using it via internet or something, and each of these nodes would have edges that would be either labeled, you in your sense would say that connection might have any kind of problems versus any kind of safe connections that you would say.
I would say you're labeling the edges by how strong the connection is, and you're labeling the nodes by how safe, by whether the node is potentially sick. Yeah. So and then you can see like how far away is the danger from you. And
Right.
yes, it is based on who is using the app, and it is not requiring that you're always on the internet. I mean, we went and built something where we use Bluetooth to go and have phones talk to each other to find out how far away they are. So we don't require constant internet access.
Right, right. And do you use any kind of like, I think is that kind of a distance approach? So for example, if I'm sitting on the table next to you or behind you, would you be using basic distance based approach of like how far are these connections? Are they 6 feet away or are they 10 feet away or just 2 feet away? How do you label them or change the properties of those edges? Is it a distance metric or something more than that?
Yeah, so we actually use a combination of distance and time, but the way we measure distance, one way we measure distance is actually fairly standard. A lot of other people use it. It's just based on the inverse square law of the Bluetooth signal strength. So for example, if you have the Bluetooth transmitter and you go twice as far away, then the signal drops by a factor of 4. And you can use this to estimate how far apart two phones are very roughly. And the key is, actually, this is also quite interesting. In the past, people complained that actually it's quite inaccurate. It is quite inaccurate. That's why in the past, about a year ago, our biggest thing was we had come up with some other way that you could use ultrasound to go and find out how far apart phones were. Ultrasound just meaning sounds that were made by the phone, which would go through the air, and based on the time it took for the sound to go from the transmitter to the receiver, we would multiply by the speed of sound and we would know approximately how far apart they were. That was one thing we were using. But ultimately what we found out is that none of these accuracies were any issue, because what is much more important is just who is generally in the same area for long times, not who is close for 15 minutes. See, we actually are not trying to do contact tracing. Contact tracing is only chasing the problem after it happened. We
Right.
are trying to tell you, along this network of the most likely ways to get disease to you, which are who you live with, work in the same office 8 hours a day next to, who you study in the classroom next to, all these things. We want to measure those. And so what we do is we measure distances and also times. And actually, the longer you spend, the more relevant it is in terms of the connection.
Mm-hmm. Right. And what would be the kind of an end goal scenario that you visualize, if at all? I think as of now, I assume, correct me if I'm wrong, but you would still face an issue of people downloading this app, and trying to convince them would be a different kind of game. I think that surpasses the idea of science or engineering, I think. But what would be an end goal or a best case scenario that you have in mind of this app? How do you visualize? Like, let's say I hypothetically make sure that every person on the planet has downloaded this particular app. What would be the end case scenario or best case scenario that you have in mind for this app?
So for us, that would be around people understanding the truth, which is that downloading this app reduces your own chance of getting sick. Now, notice, like, this might seem very trivial. Like, why do we care about this? Well, the reason is because the truth is downloading any other app doesn't really reduce your chance of getting sick. It reduces other people's chance of getting sick. That's actually one reason why the apps weren't working. The point is, people are selfish. There's also game theory in here, not only network theory. So for us, our biggest goal is just establishing that scientific case for, we have just invented a different mechanism for how you would control a disease, which is entirely powered by selfishness, right? Our entire system is, if you're a selfish person who doesn't care about anyone else, you still want ours, because ours helps you not get sick. But if you're a selfish person who doesn't care about everyone else, normally you just go infect other people in a pandemic scenario. So our biggest goal with the end game is just build the scientific case. The scientific case builds into actual deployments in some regions. The deployments build into media coverage. We actually would like that by the end of however long it takes to do all this work, that the whole world understands there's a new way that you can actually avoid getting sick. It's really powerful. Do you want it? Of course. And let me give it another example. I mean, one of the end games we care about is, suppose there's a terrible disease like Ebola. Right now, we're lucky. COVID doesn't really kill everybody. Ebola is really scary. The fatality rate is very high, over 50% sometimes. And it's also disgusting while you're dying, right? It's a hemorrhagic fever. There's like blood and all that stuff. It's bad. So we did some very simple, informal surveys, just asking people, imagine that there was a disastrous, disgusting disease with 50% fatality rate. Would you want to download an app that helps you know before it gets to you as it's coming? How many people want this? Like, yes, definitely. Like, you just asked the question, how would you get someone to install something? By making something they want. You know what I mean? Like, you could just go and make a simple app which has one thing that it does, helps you not get sick. Now, let's do a contrast. If you change the question to disastrous disease is coming, would you download an app that is designed to help you not infect other people after you have already been exposed? Do you see what I'm saying is different here? Because the standard way to control these diseases is, after you've been exposed, oh boy, you better be put somewhere. And actually there's some places in the world where, if you're suspected to be contagious, they'll put you in some place, like a quarantine camp or a special location. Actually, people are scared. Do you know what I mean? Like, what I'm trying to say is, like, we have actually cracked the code of change it from after you're exposed, stop the spread from spreading, change to before you're exposed, let the person run. And now suddenly the end game becomes much easier. As long as people understand that this is simply the first the first paradigm that was ever made that can help you avoid getting sick, then you actually want it. And now the second piece, suppose now you have the app because you want the app. Suppose the app tells you Ebola has struck someone 7 degrees of separation from you. So you spend time with someone, they spend time with someone, they spend time with someone to 7. You might not be so scared yet. But then the app tells you, like, a few days later, now it struck someone 6 degrees. 5 degrees, 4 degrees, 3 degrees. What would you do? I mean, what would you do
Yes.
if you found your
Yeah.
thing saying that it
I
struck
would.
3 degrees? What would you actually do?
Yeah, I would definitely take some actions of downloading this kind of app, or at least
Hey, look,
doing the best I can do. Yeah.
oh, sure. But what I'm saying is that second step is, let's assume you have the app downloaded because you wanted it, right? Now,
Right.
suppose the app is telling you it's getting so close. What would you actually do in your life? If you
I
found
would
out that Ebola has got 3 away from you, what would you actually do?
I would try to I would mitigate those kind of connections that the app would be saying that if I'm making this connection and it is traveling across that direction, or maybe let's say if I'm sitting in an office and the app says me that this connection is along these connections the virus is being spread, then I will stop going to the office or maybe do something that helps me cut off that connection.
Okay. And if you do this, you want to do it. No one had to tell you. The government didn't have to tell you do this to protect everyone else. You just did it selfishly. That's
Yeah.
fine. And if everyone starts behaving this way, what happens to the spread of the virus?
It can like it gets smaller and smaller. Yeah, people will be
Yes.
cutting off those connections
Yes.
itself.
So
Yes.
what I'm saying is that what this has just done is that for the entirety of human history, what people were trying to do is take the people who might be sick and everyone else and separate them. But they were always focusing on the people who might be sick and trying to make sure they didn't spread it. This invention just says, let everyone know how far away is that danger. And then as it
Yeah.
gets so close, these guys just run away. There's
Yeah.
two ways to separate the two sets, A and B, you know? You don't have to only do A. Let B run away. That's it.
Yeah. Yeah,
Yeah.
I think this you have kind of reversed the incentives. So
Yes.
rather than saying you might be doing good to somebody else, now you are saying you are doing good to for yourself. And I think this is one thing that I learned even from one of the TED talks that I was listening to some time back by a person called Dan Ariely, I think. And it was a similar thing that he mentioned, and this is something very interesting is they used to have these kind of stores like Walmart used to have this checkbox at the end of receipt that they would say, check this box if you want to donate your money, and nobody would really care to check those box, right? And instead what oh, sorry it was the license plates. So the license registers, so the license card that we get as a driving license, they would have this question, right, where they will ask, check this box if you want to enroll in the organ donation program, and nobody will normally do that. But what they changed in the forms was saying that check this box if you do not want to be enrolled in the organ donation program, and nobody checked. So everybody by default was enrolled in the organ donation program, and nobody would realize that, but nobody would mind that. So technically, 90% of let's say 100% people would be enrolled into the organ donation. So it's like understanding those kind of key techniques to understanding human incentives really help, because ultimately I think both the apps are doing good, but you have kind of a very nice way of incentivizing people, and also the approach is slightly opposite. You are trying to mitigate the spread of virus from a way how it spreads itself. So yeah, that's
Yeah.
very cool.
Yeah. And actually, something that you can say, like related to that, is that's where the game theory comes in. And it's also analogous to how this free market economy works. Free market economy assumes that people are greedy. It doesn't assume that everyone wants to go and share. That's like the communism idea, right? Socialistic
Right.
idea. The capitalism is just, yeah, you're a greedy person, just want to maximize for yourself. But how come it allocates the resources somewhat efficiently? Well, it's because somehow the rules of the game were set up so that all these greedy, selfish people, somehow it actually contributes. And what we just did is for the disease, for like pandemics, in a pandemic situation, everyone's also greedy and selfish, unfortunately. And so, how can you go and change the rules of the game, or give a tool that facilitates this like efficient, more that gives this more efficient type of market? That's what this is about.
Right. Yeah, this is really interesting. And okay, trying to zoom out a little bit of NOVID, but still on the idea of founding a startup is, I always wanted to ask this question is, you have your whole background has been fairly theoretical. Even from a mathematics perspective, you have been involved into theory, and you have been fairly into research, being PhD student or being a professor. What kind of challenges have you noticed from just an overall engineering perspective while trying to map theory into practice? And I also learned in one of your other podcasts was that you yourself have a fair deal of experience in programming. You built yourself a game, I think, in your high school that was built on a very DOS system. Very, I think that was a much more harder programming experience in my own sense, because we code in much more higher level programming languages right now and nowadays. But you have your deal of dealing with programming or implementation of any kind of ideas. What kind of subtle things that you have learned as a senior researcher that you would consider worthwhile sharing, of mapping any kind of idea or theory, or in your case algorithm, from theory to practice? You can take your instance with the NOVID app or any other kind of instances that you have used that most people won't know about.
So I think what I would say is it's best if the theoretical advance is pretty simple. When I say simple, I don't mean that it's standard. In fact, the thing I just shared with you about just reverse incentives, let you know how far away is the disease, that's simple. But for whatever reason, almost nobody, or as far as we can tell, nobody thought about it. So there are things like this. But because it's simple enough, it's robust to the real world. If you have a too delicate of a theory that requires all these things to work and all these parameters to be right, chances are that the real world will be just too messy, and then it just won't work. I mean, our system has to work even if there's people who don't know how to read. There are countries in the world that we care about where a lot of people don't know how to read. Well, they don't know how to read. Now, maybe some of the things will break down. Maybe it tells you to do something and you don't do it. That's what I mean by robust. So our mechanism is so robust that even if a good fraction of the people don't understand it and don't use it, it still works, right? So my point is, the first thing is that ideally the theory, if you're trying to apply the theory to the practice, ideally is robust enough, and it's not fragile. It doesn't require so many things to be just perfectly lined up. Ideally, it's simple. And then the other things are just to understand that in the real world, all these things will come up. You'll get funny things like you're trying to deploy somewhere, and then the person that you're working with goes to jail. Like this happens, you know. And this is just that doesn't happen in your theoretical research paper, you know.
I'm
But
sure.
this is the real world, and I think I'm just used to that.
Ah, right, right. Okay, okay. That's that's pretty. I mean, the way you say it is pretty much like that's not definitely normal. And any kind of researcher who is into theory would definitely never consider in these kind of problems, like if a person would go to jail who is in charge of the deployment. Yeah, yeah. That's pretty interesting. Okay. And jumping back to the idea of many of the people who are listening to this podcast are into AI or machine learning research, and which is one of the I would say as of now we have a lot of hype around the idea of AI or machine learning applications that we see much more involved in our day-to-day lives. So I want to understand from you, from a mathematical perspective, is there something beautiful you find about machine learning or artificial intelligence from a strictly from a mathematical perspective, not from an application perspective? But if you look at those algorithms, I think ideas like neural networks or convolutions, I'm not sure, feel free to say if you have not explored those topics, but ideas of convolution or maybe transformer based models which are normally used in language processing, is there something beautiful you find about these kind of architectures which have a very strong base to mathematical? I would say they are basically mathematical structures. And if so, what is that thing that how do you see these kind of architectures from a mathematical strong perspective?
Yeah. So first thing I'll say, this is not actually the main thing I work in. However, I've been around enough people who think about these things to know enough to be dangerous to myself. But what I should say about this is, I think it is very interesting that these are somehow some ways of hopefully extracting some kind of a signal from a very complicated set. I've actually thought a little bit about this before, like even how the brain maybe works. It's like we're getting all these input signals, and then what should you do with the signals? Just add them? Well, you want something more complicated, right? Because ultimately, mathematically, if I think mathematically, if you're just adding functions, especially if you're adding some, especially if you're adding some functions which are of pretty simple signals, you're not going to get a rich enough space of things that you could hopefully do something with. And so to me, it seems quite interesting that there can be a bunch of building blocks that are rich enough that if you combine them maybe in a few layers, you can actually represent very sophisticated functions. I mean, I think of this more in general of just like, if I'm trying to build a fancy function, a complicated function, and the only ingredient I have is something very simple, at the beginning you might think you can't build that complicated of a function. But it turns out that if you just have slightly complicated ways of combining signals together, then once you start chaining them, you get something very rich.
Hmm. Hmm. Yeah, yeah. I think that, yeah, that's a very nice definition, and I can the way I'm the reason I'm smiling is because the way I look at this definition is how you have literally seen the whole definition from a strong mathematical perspective, which is fairly interesting, because most of the definitions that I normally talk to people who are into AI or machine learning, they describe the whole idea of how we are trying to map inputs to outputs is fairly very different. So yeah, yeah, what you said is definitely very interesting. And is there something to be said? Because the reason I'm asking is you deal with a variety of age of students, from very young students, high school students, middle school students, to college students over here. Is there something you could say? I'm not sure if you are the right person to ask, but how much in-depth mathematics is truly needed for any kind of computer science research or AI or machine learning researchers? Because this is one thing I often get asked, and even I would say my base, it was very later into my grad study or undergrad study that I started realizing my basic knowledge of linear algebra or calculus, or even in general discrete mathematics, is fairly inapt. So we use these kind of models every now and then, but when we talk about any kind of innovation in these kind of research, we are strictly bound because we don't have that much amount of knowledge to tune or tweak these kind of models. Feel free to say if you won't be the best person to ask, but how much would you say a person should know mathematics if they are getting started into
Hmm.
this domains?
So again, although this is not what I definitely do myself, I am actually at Carnegie Mellon University, where there's quite a lot of people who do think about these, especially students. And oftentimes what I advise the students is make sure you have a very deep understanding of linear algebra, and
Hmm.
ideally also of statistics and probability. Because you actually, I found it quite interesting that you also mentioned linear algebra, and you mentioned that first. Because if you start thinking about a lot of these models, and once you start thinking about covariance matrices, and oh, it's a matrix, like what's a singular value decomposition? Like suddenly all these linear algebra stuff comes out. And I
Yep.
will say that unfortunately some people learn linear algebra in a very mechanical way, where they say, okay, I got this kind of problem, this is how you solve. But if you don't understand the concepts of it, once you start doing something more sophisticated, you start to wonder exactly, why do I invert this matrix here? And why do I take those eigenvalues? You know what I mean? It's all just some soup. I just do it because I'm supposed to. But if you have an understanding of it, then actually it makes sense. And then you can hopefully move on with more sophisticated things as they're necessary.
Yeah, yeah, this totally makes sense. And just a funny bit to that was it was only a few weeks back, and most of the collaborators I have are radiologists. So when they they do understand the basics of AI, and we were talking about a certain topic where they said, Jay, do you know about how to calculate eigenvalues of a particular matrix? And I said yes. And for a moment, I forgot how do I calculate these kind of eigenvalues and the eigen vectors. And that was the point I realized I need to furnish my basics in mathematics, because I was strictly relying on the internet resources for doing that. So yeah, definitely, I definitely agree to that. And so talking okay, again, zooming back to the whole idea of mathematics, is what is that one problem, or even one more problems that you think are still unsolved and that you are particularly interested in solving? Because it could be, I think you already mentioned that much more of a combination that interests you in a topic, the theoretical pursuit, and of course if that problem has an application and application oriented endpoint to it. So what is that one problem that you think in any kind of subfield of mathematics that you are currently working on, or even if you're not working on, you're definitely interested to explore more, that could have any kind of incentives for you to work on?
Okay, so I should say that right now most of the work that I'm working on is fairly applied. So
Yeah.
I would not actually name a theoretical problem at this point. I mean, the applied problem I'm actually interested in is this combination of what you can do with network structures and also, let's just say, health data. That's just because that's where I happen to be right now. Well, and also it's something that could have a lot of impact. What do I mean? Well, we have always had health data, and I mean, we have, there's all this like innovations in digital health and all of these things that you could have health data on the person. But what we have just started to open up is this opportunity to even know about the interactions between people. And the reason why this is relevant is because disease is transmitted by contact. And so now if you could combine network structure of people interacting with each other together with disease information, this is a general problem of how can you identify the emergence of new diseases? How can you track or predict what might happen with a disease? I'm actually, I'll probably have to learn something about machine learning and artificial intelligence, right? Machine learning, where in the sense that I'm looking to combine just that information that you have personal health from all these signals. Maybe you have some audio signal that you got from coughing into your phone. Maybe you have some temperature signal you got by using the smartphone camera to take some picture of your forehead. I'm just saying you have all these signals that represent information about a person. And there has been a lot of innovation around how do you use that signal information to help tell the person something about their health. What I think is that the next level is if you combine that together with the network structure. Because now suddenly, if you both have like the temperature information and the actual network interactions, you might suddenly notice that in this country, somewhere on the opposite side of the world, some mysterious propagation is happening. I'm talking about the cross correlations between many people who are interacting with each other. Do you know what I mean? Like those are things that were not accessible before. I always try to think, what can we do that is potentially new? And this was just not accessible before. Before we only had persons data. But now I'm saying persons' data together with who they are around. And I want to do the whole thing anonymously. You mentioned that early on. I don't actually want to run any advertisements. That's not interesting. So the point is I wanted to build a system by which we can actually anonymously find out that there's like this network of stuff, there are these various symptoms, there's this mysterious new disease, how fast is it transmitting, all of these things.
Right. And I think the idea of mobile health, like having Apple Watch and a lot of other devices which are trying to calculate a lot of vitals of human body that wasn't available before, I would say.
Yes.
So I think
Yes.
those would play a really nice role into these kind of
Yes.
applications.
Yes. So the way I see it is those are great, but they didn't use the network. Again,
Right.
I'm this
Yeah.
combinatorialist. I do network theory. What I say is that's great, but that's like as if you had computers with no internet, which is like how I
Right.
grew up, right? Like maybe like not quite how I grew up, but yeah, actually in the 90s, a lot of us just used a computer as you plug it in the wall, and you have a
Right.
computer. And then at
Right.
some point, people got the dial-up modem, which was a big deal in our family, and then you start being on the internet, and eventually now we cannot survive without the internet. But what I'm saying is like, why not do the same with people? Right? What I'm saying is that the Apple Watch and all those things, those are the same as the 1970s computers. Now
Yeah.
imagine you also had anonymously. Anonymously is important. All this information about what's going on. Wow, who knows? Maybe we could even make the entire flu just stop. Like things that were unthinkable before, you could
Right.
potentially knock out.
Yeah, that's really interesting. It's like as of now, what I see the NOVID app is you're trying to predict the spread of virus, but in this case, the next step would be predicting itself the origin of virus. I
The
mean,
origin of
you
virus.
would you would
Yes.
have you would in this case in the idealistic scenario you would have predicted the like you would have predicted the spread back in
We would have
February
found
or
out, yeah,
January. Yeah,
yeah.
yeah, yeah.
Or rather, like even today, we might potentially help to identify variants. Like if you
Hmm.
start to notice that, I mean, there were characteristics of various variants, such as some variants had the property that they started to infect people who had already been infected before. That's clear, right? Then you know something happened because now there's a person infected twice, and they're around other people infected twice. This is new, right? Or you might find out that this particular variant infects everyone in the household. They're like earlier on, not everyone in the household will get infected. Suddenly, statistically, the whole household is getting infected. What happened? Right? So I'm just explaining that these are all things that could be done. And I think that the interesting frontier is how do you combine all of this? Of course, in order to get there, we need to go and develop this particular one we're working on right now.
Hmm. Hmm. Yeah, yeah, that's really interesting. Yeah, that's really interesting. And one other question that I want to ask, which is slightly on the philosophical aspect, and feel free to shoot it down or answer this perfectly, was you have a great deal of experience working on variety of mathematical problems, and combinatorics being one of them. A question that I always got intrigued, even as a young student and even right now as a graduate student, is we see a lot of patterns in nature, right? We see a lot of patterns in nature around us, in the living objects and also in non-living objects. And it is very easy to find a direct correlation to these patterns to mathematical norms. For example, one of them is very popular is the Fibonacci sequence, right? We see a lot of patterns in these kind of natural happening scenarios. For example, flowering of artichokes or something like petals of flowers which grow along the kind of a Fibonacci sequence. And I keep on reading these articles that a lot of things around the world happen according to mathematical equations, or the other way around, that the people who have invented these kind of formulas must have taken inspirations from these natural scenarios. Do you think that there is a possibility of having a mathematical structure to almost everything we see around us, as in everything that is associated from very of the smallest particles to whatever events are happening, have a strong relevance to mathematical structure, just that we don't have discovered for every and every other thing that happens around? And first of all, yeah, I'll let you answer the first question, then I'll build on the second one. Yeah.
Yeah. So I think that some of those things have nice structure, like the Fibonacci, but the Fibonacci one I can understand because it's like, how do you make the next thing? Well, you take the previous thing plus the one that was there before,
Right.
right? The 5 is equal to 2 plus 3, 8 is equal to 3 plus 5. Well, that was very easy for me to explain to you. It was just a very short sentence saying, the way you make the next thing is you take the previous one and the one before and add them together. Actually, I think that that type of nicely encoded structure happens often in nature or where else because it's very information concentrated. It's information dense, a very, very simple way to describe a very complicated thing. Somehow, it seems like there are also things that are very messy. For example, when the Big Bang happened, things went everywhere. I don't know if there's a nice way to describe that. It could have been that very minute variations in what was going on at the time of the Big Bang caused, as the thing expands, then you have a galaxy here. You have this slightly more dense area. It attracts a lot of matter. I'm trying to explain that there's also very chaotic things. I don't expect that there's a nice mathematical description of how you specifically put all the galaxies in the universe, right? So what I'm saying is there's some things which are messy, and there's some things which are very, very clean and tight. Another thing is like the human biology. How in the world does our brain work? I mean, how do all those connections come? I don't know enough about this, but my understanding is connections actually form during your life, and your connections and my connections are different. Actually, I think that's probably true. Even though I'm not an expert here, I think it's probably true that if we went and mapped your neurons and my neurons, that my neurons would have different pattern than your neurons.
Right.
That's my guess. But now, well, how did that evolve? That was even through the random, just like how the Big Bang was based on random stuff being scattered around, and then boom. Similarly, it was when I was a baby and growing up, my brain was exposed by different stimuli, different random stimuli than yours, and then went in a different way. But what I mean is like that, I don't expect there will not be a nice mathematical description for why that happened. Right? So the way I see it is that some things will happen nicely, some things will not. But there might be a pattern to the things that are happening nicely. Those things might be because they happen to be the most dense ways to express in the DNA how to make that sunflower or how to make those petals.
Right. So yeah. So if I understand correctly, it would be, there would be still some patterns that mathematics can explain, but it is just not easily interpretable by us. So we can interpret Fibonacci sequences, but if at all there was some kind of a mathematical equation that can explain my neural structure versus yours, we won't understand, even though there could be a pattern to that randomness.
So the way I'm seeing this is actually like if we talk about the neural structure, I raised that example on purpose. It's that somehow that's an example of me, for me, of I mean that's an example from my point of view of a very complicated function. Like these neural networks are basically encoding very complicated functions, and somehow that brain mishmash of neurons is able to do such thing. But then there are much simpler functions that maybe are the ones that come from what you can get from these petals forming,
Right.
and in those particular cases, those do the job. And since they do the job, it's the simplest possible. Basically, I'm saying it's simple enough. It does the job. Doesn't occupy much space in the storage, like the DNA storage. So that works. But maybe there are
Right.
some things that are more complicated. Maybe the brain is not so simple as say this neuron just does what the previous neuron does plus the previous one, right? That you don't
Right.
have an interesting brain. Then you start to need more complicated functions.
Okay. Okay. Yeah. Let me notch this question a little bit up, and I think you already answered this question, but it's worthwhile just asking your opinion on this. Is a lot of hype around the world of AI talks about, and I think these are only news media articles, not even serious researchers try to question this thing, which is, can AI truly model consciousness? And I want to learn more about you, because if we boil down that question, it just boils down to the idea, can we really model consciousness from a perspective of mathematics? And I just want to learn, because feel free to take this question or go along the line of philosophical perspective, because I think we don't have the enough research or standards to answer this question. But do you have anything to really comment on these kind of things, like AI itself is kind of just an implementation of much of mathematical functions? If at all the question comes down to, can mathematics really model consciousness, what would be your take on that?
So I guess the question is about, to me, like, there's a question of what do you mean by consciousness, or do you just mean, can AI make it so that somehow that thing I'm talking to, from my point of view, I'm talking to it and it's acting just like a normal human being. To me, that's different from consciousness. To me, that's like indistinguishableness from talking to a human being. But in terms of consciousness, I guess my interpretation of consciousness was just what I have, which is I feel conscious, but that's not to do with how you are interfacing with me. Even if I was saying absolutely nothing, I would still feel conscious. So
Right.
which what are you referring to? Are you referring to like the AI making it so that if I talk to that person, my point of view is could be a real person or could be an AI, or are you talking about really this like consciousness thing, which is very complicated?
I think the idea of consciousness, at least from an AI perspective, is the realization that itself, like, for an AI system to be conscious enough, it has to understand what it itself stands for. So I think when we talk about human consciousness, it's the idea that I understand what I am, right? What do I carry? What are the kind of things I carry? Rather than just having just a set of information, I have set of other non-physical traits that would be associated that I know myself of. So I know how much of
Ah,
a uh, emotional person or an angry person I would be. That is something that's just not visible, right? That's not something I put on my resume, but only I am aware of those things. So I think those really boil down into consciousness in general. And when we talk about these consciousness idea into AI, is the fact that I think these AI systems are churning out decisions. Are they really conscious of the decisions they are making, or are they just mapping inputs to outputs? So that is the idea of, I think a lot of people talk about consciousness, and the idea that can it make those kind of non-conscious decisions versus conscious decisions. So those are the things I think a people like to brainstorm. There is no strict literature that really talks in depth about these kind of things, because again, there is no one structure to this. But I think that boils down to the question is, like, can mathematics do that? Can mathematics really have the bandwidth to accumulate these kind of parameters into one model?
wow, that's a deep question. I actually don't know the answer. I mean, because to me, I guess I don't know enough about how brains work. I don't even know, for example, if if a mouse is conscious in that sense, or like a fly. I mean, I often wonder how can you have much happen in a brain that is fly brain, like how big, that small. And if I go and compare to the human brain, it's a huge reduction, right? And so I
Yeah.
wonder, like, is the fly conscious? Is the earthworm conscious? If the definition of conscious is understanding that I'm a fly and I can do these things, or is it just simply responding to stimuli of like light there, go that way? Do you know what I mean? Like, I actually just don't
Yeah.
know the answer. I think it's an interesting question, but I have not thought about it seriously before.
Yeah.
I mean, actually, what
Yeah.
do people think? Do they think that flies are conscious?
Um, I would rather have to ask them, because I think even for all these conversations that I engage in with people about consciousness and relating to AI, the bottom line always remains the same: is we have to define what consciousness is.
Hmm.
So I mean, I could easily come up with an definition where I can say a fly is also conscious, and Po sitting in front of me is also conscious. So it really depends on the definitions that we are trying
Hmm.
to create. Because yeah, I yeah, even like I said, I don't have a strict answer to that, but it's worthwhile because many of these open problems we see a lot of coming down from the AI community are much more open-ended questions, and we realize we don't have explanations for them. And one of the other topics is interpretability or explainability. We see these deep learning models doing things uh, that human decision making processes were worse at, or maybe just bad at in over the years. And now that a lot of people are starting questioning, right, like we want to question, there are these GDPR regulations and all those things where they tell why this deep learning model did things, and now we are questioning, okay, why did it do that, and we are trying to question these non-linear equations.
Yeah. So to me, the thing there would be, I would first want to know more about what people think about flies, because I have thought about that before. I have thought, oh, like if the fly is conscious, okay, how about the earthworm? I think they have even less neurons. Or you know what I mean? I'm actually quite curious
Yeah,
how this is all thought.
yeah, same here. Okay, yeah. In that case, I just have one last question, which is strictly for the audience. That most of the people that are listening to this are mostly researchers or graduate students. So, what would be your one piece of advice, or maybe just two pieces of advice, if you would like to, for people who are starting off the journey into mathematics and they are on the verge of exploring mathematics from a student's perspective? They might not have the exposure to what mathematics can really provide them, versus they are just trying to learn more about exploring, if he or she would like to get into research, versus just understand mathematics from a very surface level perspective. What would be an advice to those kind of people you would give who are starting off the journey into mathematics, or in general even computer science?
I think my advice would be that learning is interesting. I don't mean machine learning. I mean just like learning yourself. The more you can learn, the better. If you're not in a hurry to go and get a job, you don't need to. Go and learn more. You go to graduate school, and the more that you learn, eventually, the more you can possibly do something with. Uh, that would be the first advice is like learn stuff. My PhD advisor once told me that your schooling times, those are your times, that those are your opportunities to learn. Afterwards, you have to work, right? And so to learn. And then the second part would be hopefully find things that are big to work on. Whether you start it yourself or whether you join someone else to work on it, both are fine. Actually, starting it yourself is pretty hard. So find someone else to work with is also probably a pretty good solution. But whenever you find things, ideally work on things that are bigger or that matter, because you only have one life to live anyway. So somehow learn as much as you can, and then do as much as you can with what you've learned.
Right, right. Yeah. That's really great. I think yeah, focus on learnings first, and then figuring out on things where you can apply those learnings would be something very useful. Yeah, that's all I had questions for you. I think this was a very interesting podcast because I never had a person who would have a pure background in mathematics and have such a diverse portfolio. So thanks a lot for being here, and I think I'll leave a link to your the startups that you are working on, and also your homepage, so that people, if have any questions, they can directly reach out to you. And I think also a link to your YouTube channel, because I think that's really very intriguing and fun thing that they can do definitely while they are on YouTube. So yeah, thanks a lot for being here, and hope people listening to this podcast find this useful.
Great, nice talking to you.